Good evening, everyone. Thank you for coming, first of all. Looks like a really good turnout, which makes me happy on my day after work. For those of you that don't know me, my name's Matt. I was a vehicle dynamics engineer and technical director last year for the project. This year, I'm on placement at Warwick Racing in Formula E as a race and performance engineer. I'm just put together a little presentation about suspension, VD, setup, all the kind of stuff that I used to do on this car and that I'm now doing in Formula E. I hope it will be informative for you guys. If you have any questions throughout, stick your hand up and I'll try and answer. I have left dedicated time at the end for Q&A, so without further ado, I will get started. The idea of this presentation is to just kind of set out some of the basics. VD is a bit of a dark art, though I do say so myself. There's a hell of a lot that goes into it. I'm going to go over the fundamentals of tires, VD, suspension, just so you guys have a bit of a starting point. If you're interested to then go and extend your knowledge, I'd point you in the direction of Eric and Caitlin, our VD and suspension leads. They are more than capable of answering all of your questions, I'm sure. We'll start with a question for the room. Some of you might have seen this while I was out of presenting mode. But what is the most important factor for a race car to get performance? Yes, Will?
Weight.
I like your thinking, but I disagree, personally. Aiden? A man after my own heart. You're right. The tyre is the most important part of the race car. So, a little bit about tyre science, and I won't get too nerdy about this because this is mostly what I do at work, and it is really, really boring. But essentially, your tyre it's your only point of contact between the vehicle and the ground. So without the tyre, the car doesn't move. You need the grip of the tyre on the road in order for the vehicle to accelerate, decelerate, go around corners, etc., etc. So grip is a really important factor when it comes to determining performance. But to understand that, you need to understand what grip is and where it comes from. So there's two main sources of grip for a tyre. So you have molecular adhesion. The rubber molecules form bonds with the stone and glue and everything you have in your tarmac. And they're consistently formed and broken as your tyre rolls along the ground. The other kind are from friction forces generated by a thing called slip. So if you imagine a tyre rolling along the ground, the tyre contact patch where it touches the ground is deforming, like you can squish a tyre. The forces that deform that contact patch are opposed by frictional forces, and they come from something called slip. So slip is really fundamental in understanding anything vehicle dynamics related. So whenever you're braking, accelerating, cornering, whenever there's any kind of acceleration, there's a relative motion between your contact patch and the road surface. And essentially, frictional forces get generated when that's happening to stop the car skating completely off the road. It's a bit abstract to kind of visualize the fact that the tyre is slipping when the car is in grip. So the way we think about it, or the way it can be rationalized, is that when you have movement between your tyre and the road surface on a microscopic scale, that's your slip. That's where your grip is coming from. That's creating those nice frictional forces that are holding the tyre to the road. When you have it on a macro scale, it's called skidding, which is when you see your big oversteer or understeer moments, the car sliding wildly across the surface out of control. When it comes to braking and accelerating slip, that's quite difficult to quantify in a meaningful way. With cornering, especially on your front axle, your steered wheels, it's a little bit easier to understand. So slip angle is an easy or easier way of demonstrating what slip is. So when you have a tyre traveling around a curved path, a corner, there will be a difference between the direction that the tyre is pointing and the direction which it's actually traveling. That difference is your slip angle. And the physical manifestation of that is, you can see in the diagram, the lines represent groove of like a tread block. The tread block deforms at your contact point. because of the friction forces generated by slip. And a good way for you guys to sort of understand that is if you run your hand along a surface and try and go around a curve path, you can feel your palm twisting and deforming, which is exactly what happens to your tire on a racing car. Now, we can get really, really nerdy and into details about the grip limit of a tire, the effective temperature on a tire, the effective compound on a tire. And all of that information is in tire testing documents, which I'm sure Eric can point you towards. He spent a lot of time looking at them already. At the point of those tests essentially is to give you graphs like this, so you can understand that for a given slip angle, your lateral force is sort of analogous to your cornering grip, and each of the forces or the loads alongside tells you how much vertical load you have on your wheel. So if you have an aero car, like the faster you're going, the more vertical load. So by studying these graphs, you can work out what sort of slip angles you want to get maximum grip. You can work out what temperature you need your tires to be at to get them in window. So yeah, there's some really good information in those reports if any of you are interested. So yeah, as I talked about earlier, one of the two sources of grip come from the tire's interaction with the surface. So the surface that the car is running on will have a massive effect on the grip level, on the lap time you can achieve, and on the rate of wear that you have in your tire. So we split up tarmac roughness measurement into macro and micro. So the way we do this in Formula E, Formula One, any top-level motorsport, we have machines that you literally drag along the track surface, and it will measure the surface and tell you. Macro effects is when you have big gaps between the peaks in the road surface that are anywhere from 100 microns to 10 mil. So that's sort of, you can visually see if a surface is high macro or low macro. If it's really nice and smooth, it's low. If it's full of stones and horrible, it's high. They affect your slip forces. So there's a diagram there that sort of tries to explain that as the peak in the road deforms the tire, you get a force that opposes that deflection, which is where your grip comes from. Your micro is looking more at the smoothness of those peaks, which determines how the surface of the rubber forms its molecular bonds with it. So when you have rough tarmac, you get lots more grip, but it wears away your tire faster. Part of the process of molecular adhesion is that you lose some of those molecules every time the tire goes around. And if you have a really smooth surface with low micro, you just have no grip. It's like driving on ice. And obviously, any of you guys watch F1 or other motorsports, you'll know, like, surface evolves throughout a race. As the rubber gets laid down, it provides more grip. The track evolves, which is all stuff you have to account for. One of the main areas of interest we have for tire performance is temperature. Every tire is different, the way it's constructed, the compound of the rubber that goes into it. And a very easy way of understanding the performance of the tire is through its temperature. So the diagram shows a road tire, but it gives you the idea that you have different components in the tire. You have your tread, your carcass in the center, beads, sidewall, etc. When it comes to quantifying tire performance, the two main areas you look at are your surface, which in this diagram would be your tread, and your carcass temperatures. So in the context of Formula Student with our TPMS system, we should be able to monitor carcass temperatures live. Surface temperatures, you need infrared beams, which we don't have currently. The carcass of the tire is more stable, so the temperature change is much more gradual over a session. You build temperature more slowly, and you lose it more slowly when the car stops driving. Surface temperature is much more volatile. It will peak much higher, and it will peak mid-corner, and then tail back off down a straight, and then peak again in braking. And managing your surface and carcass temperature is how you get the maximum grip from your tire. So from your tire testing data, you can work out between a given range of carcass temperatures, you will be providing maximum grip. Between a given range of surface temperatures, you'll have maximum grip in lateral, longitudinal combined, which, if any of you are unsure, is the car can be In pure longitudinal is when it's either just accelerating, just braking, pure lateral, just cornering with no brake or throttle, and combined is when you have the two. So each section of the graph shows you your pure left-hand cornering, pure right-hand cornering, etc., etc. The further away from 0, 0 you are, the more grip you have. The more grip you have, the more acceleration you can permit before the car starts to skid. This isn't a foolproof method by any stretch, because your IMU will still be recording accelerations if the car is sliding. So you need to develop a certain level of understanding of what the actual limit of the tyre is before you can just look at a GG diagram and go, yes, we have this much grip. The tyre is working. So yeah, that's the fundamentals of tyres, I guess. I won't go into too much more gory detail, not right now. The next topic I'll talk about is suspension, which links nicely to your tyres, because it's all well and good having your tyre performance metrics and your tyre working, but you need to keep your tyre on the ground, which is where your suspension comes in. So yeah, there's a hell of a lot of different parameters and design factors and setup factors that go into influencing how the suspension's working and how your car responds to it. So the first topic is geometric parameters. So when you come to design your suspension system, it can be simplified or oversimplified into a matter of thinking about points in space. Suspension is attached to the car at the hard points. So you have your chassis side where your link's attached to your car, and the outboard where it attaches to your upright assemblies. The relative position of each of those things will determine how the linkage behaves, and as a result, how much control you have over your platform and how much control you have over your wheel. So when you look at the car inside view, the two sort of main parameters you draw attention to are anti-dive and anti-squat. Essentially, what they do is they resist the car's natural tendency to dive and squat under load. So if you imagine the car traveling at a steady speed, if you brake because of load transfer and the location of the center of gravity, the car wants to dive down. It wants to transfer that load over the front wheels. Now, a certain amount of that is good. Generally speaking, if you look at our car, our front brakes will be bigger because that load transfer means you have more grip on the front end and accelerate while exiting a corner. You want to be able to control the amount of dive. So for our car, we don't run aero. We have not a huge amount of anti-dive or anti-squat. Yeah, that's the rundown of that. The front view of the car is to do with your roll centers. So again, geometric constructions based on the path that your wishbones follow. This example is double wishbone, which is what we use on our car. Depending on where your contact patch is, where all your hard points are, and where your center of gravity is, it determines where the roll center of the car is. And the roll center is essentially, you can visualize it as if you freeze a moment in time instantaneously when the car is cornering, that is the axis about which it will try and rotate. So positioning that roll center is really, really important. So I'm sure you're all familiar with the concept of moments. Depending on how far away from your center of gravity the roll center is, will determine the roll moment, which is the moment arm that's trying to roll the body of the car. The further away you are, the more intense that is. Yes, Maddie?
Is B the chassis, like where it's mounted to the chassis?
Yes, that's an inboard hard point. So, yeah, the roll center is a constant for a given suspension position. So in this diagram, the roll center is there. But if you compress one side or the other, it will move the roll center. So a little trade secret that I'm going to give out, because I think you guys might benefit from it. You can work out live with data where your roll centers are if you understand your suspension linkage, and you can quantify the understeer or oversteer balance of the car empirically with numbers, not just having to rely on driver feedback and the eye test. So by performing all your roll center calculations at every position or a series of positions within the suspension's arc, you can then work out where the roll center will be under whatever scenario the car might be in. There's front and rear roll centers. Obviously, your front and rear suspension are independent, and together those moments form a couple. That roll couple will be distributed along the length of the car, depending on how large those moments are, how far away from your center of gravity the roll centers are. So by plotting how far or where the roll couple is distributed to, you can see if the car is under or oversteering, or prone to over or understeer. If it's further forwards, you're understeering. If it's further backwards, you're oversteering. So yeah, that's something interesting that the suspension team could maybe work on with the controls guys, modeling that and implementing it into the data. The other factor to consider with your mechanical linkage is how it behaves dynamically. The whole car is a dynamic system. So we've made in the CAD, and I believe they're accessible to everybody, some dynamic simulations of, these are from WRE3. And they essentially allow us to visualize that when the suspension moves through its arc, the wheel will not stay still, essentially. As you go through the arc, your camber will change, your toe will change, which, don't worry, I will cover all of those parameters in the next section. But essentially, your goal of the suspension system is to control the wheel, to keep the tire on the ground, and to control your platform, to keep the car stable. So if your linkage has a load of camber change as it compresses, it can be good in a sense. So when the car's cornering, it will try and roll the sidewall of the outside tire will deform, and it will try and roll the tire onto its contact patch. Negative camber is good because it means that by the time it's rolled over, you then have all of your contact patch on the ground. So a certain level of camber gain is good because it means the harder you're cornering, the more your suspension's loaded, the more likely you are to have maximum grip. But if you have too much or you lose camber, you lose grip while cornering. And conversely, particularly on the front end, if you have a gain in camber, when you brake hard and the car transfers forward, your wheels sit up, which means you have as much grip as possible for braking. So this is really what I mean when I say that suspension design and VD can be a bit of a dark art, because there isn't really a right answer. Certainly not when it comes to dynamic behavior. It's a case of fine-tuning, making changes. If you can have physical testing to get some data, great. If not, you simulate and try and work out the best solution for our application. The other part of suspension parametrization is to do with your spring and damper. So these are the different ways or the different types of excitation that a car can experience. And it helps to sort of define these to choose your spring and damper values. So heave is just all four wheels going vertical, roll side to side, a difference in damper displacement side to side, which is normally associated with cornering. Pitch, forwards and backwards, which again would be associated with accelerating or braking. Warp is, as Dave Cooper will tell any of you, cars can be a bit weird, particularly welded chassis. There will be a difference, usually diagonally across the car. And warp is a kind of measure of that. If you set a car up and get it on the ground and don't sort of play around with push rods and the setup as a whole, there will be a very noticeable difference diagonally across the car in the load that each of the wheels see, the ride heights, etc. So if you've got a car that's heavily warped after you've set it up, it's going to be a bit unstable and asymmetrical depending on your cornering conditions. All of these excitations will have natural frequencies associated with them. So obviously you don't want your suspension to be loaded with those natural frequencies to avoid the big gain in amplitudes. So We have K&C testing, which is available to us as Formula student teams, like it is to pretty much everyone in motorsports, where you put the car on a big 4-post hydraulic rig and they shake it, basically. And it will tell you all of your natural frequencies, which allows you to select your spring constants, your damper values as best you can to avoid those natural frequencies and to control the platform as best as possible. Rig testing is great, but it's only kind of part of the equation. I'm hoping that we'll get to go on the Multimatic rig this year to have that baseline data, and then from that you can go test the car, see your physical data correlation, incorporate some driver feedback. You can change the balance of the car with your springs and your dampers. But yeah, on the topic of changing the car's balance, finally, we'll talk about setup, which is a fascinating topic and another dark art. There isn't a right answer. Any driver, professional driver, will tell you a different optimal solution. So the first key concept to understand is camber, which, as you can see in the picture, describes the wheel leaning towards or away from the car when you view it from the front or behind. Negative camber is when your wheels are leaning towards the center of the chassis, which is generally what we'd be running in a racing situation. So yeah, negative camber is what we would have. It's desirable in a racing context because as you're cornering, your outside tire, which is the most important tire for determining cornering performance, that's where your grip comes from. The contact patch will try and roll over, and by putting the wheel angled towards the car at neutral or statically, when you put those loads through it, it then means that the contact patch is fully on the ground during high-speed cornering, which gives you the maximum amount of grip. There are some downsides. It can increase your tyre wear, and statically it would reduce your straight line acceleration because your rear wheels are not fully on the ground when the car's in a straight line. But in a circuit racing context, that generally isn't super important. Neutral is good for drag racing, for example, because it means your rear wheels are fully on the ground when in a straight line. There isn't really a reason why we'd want to be running zero camber in our race car, or any circuit racing car for that matter. Positive camber, again, for the same sort of reasons, never really used. It gives you that smaller than baseline contact patch at neutral. It's sometimes used for like lorries and stuff because it means when you put something really heavy in it, it sits down to zero camber. But again, please don't use this in Formula Student, ever. So yeah, this is a kind of visual representation of what I've been trying to explain with camber thrust and the tyre deforming as you put cornering loads through it. So yeah, choosing your camber angle is again a bit of a balancing act when you don't have great data acquisition to try and work out where your wheel needs to be neutrally to put you here with all your grip when you're cornering. Yeah, caster is the next thing. So again, that describes it describes the inclination of your steering axis as you view it from the side, from vertical. So positive caster is leaning towards the rear of the car, negative towards the front. A lot of setup parameters are kind of about finding compromise, and you can make a case for a lot of things. Caster kind of isn't one of them. Positive caster is the only thing that we should ever be doing in a racing car. So it creates a self-centering effect, which, as I'm sure most of you, if you drive road cars, it's a nice confidence-inspiring feeling knowing that if you let go of the wheel, it will return to the straight-ahead position. It also creates a sense of weight and feedback in the system, which for a racing car is really, really important. It can also create a jacking effect, which is if you've ever been on a push bike and you try and turn the handlebars, you can feel the bike sort of moving itself away from you and up underneath you, which is what happens with the car. So when you turn a car with positive caster, it will sort of sit up and put load on the outside rear wheel, which is exactly what you want for cornering performance. Yeah, the downside is heavy steering, but we're a race car. We don't really care. And in like bigger, heavier race cars, you'd have power steering to counteract that. Negative caster is negative. Please don't use this, ever. Essentially, you introduce huge instability into your steering system. It makes it very light, which would be good for, you know, like going to the shops or something. But at high speed, you get wobble in the steering wheel. It gives very little feedback to the driver. It would be a mess in a racing context if we had this. Zero caster is just kind of, yeah, it doesn't have all of the negative effects of negative caster, but you don't have any of the positive effects of positive caster. It just kind of doesn't really do anything. So again, don't use this. Kingpin inclination is another factor, which is less to do with setup, but I think it's important to touch on. The diagram shows your kingpin axis, or it shows the kingpin axis for WRE3. Essentially, your kingpin axis, sometimes referred to as steering axis, is the axis about which your steered wheel rotates. So it's formed by just creating a line that goes through your upper ball joint and your lower ball joint, which the upright turns on. Positive kingpin inclination is when it's leaning towards the car. This is what we normally run with. It creates the same sort of self-centering effect as caster, just in a different plane. But it can have an effect on the camber gain in your loaded outside wheel, which, like a lot of things in setup, if you increase your self-centering effect with kingpin, you mess up your camber gain of your outside wheel, which reduces your cornering grip. So it's about finding the balance. And with kingpin, because it's sort of set by your mounts, unless you're making multiple sets of mounts, it's set in stone from when you finish your design. So it has to be considered and then just kind of left alone. It interacts with the scrubbing radius of the vehicle. So scrub radius is, again, really just a moment arm about which the braking forces try and act on your steering. So if you have a big scrub radius, when you try and brake the car, the driver will feel that through the steering wheel. If you're not braking in a perfect straight line, the scrub radius will allow those braking forces to try and turn the wheels. So again, scrub radius is a design parameter that's set during your suspension design and then pretty much left alone. It will change a little bit here and there with some setup tweaks, but it will always be in the ballpark that you determine. So yeah, kingpin design is really about finding the right sort of compromise. Sometimes less in our case, but more in sort of road cars or GT race cars, you're packaging limited. If you've got to fit your wheel in a closed space, there's only so much you can do with your mounts. But yeah, that's a design aspect that's been left in some very capable hands this year. The last main parameter I'll talk about is toe, which is, when viewed from above, are the wheels pointing straight towards themselves or away from each other. Toe will have varying effects depending on if your car's front wheel drive, rear wheel drive, all wheel drive. And because of your effects of bump steer, when the car's dynamic, it's not a fixed thing. So toe in on the front wheels is when the wheels are pointed together, and that will make your car stable in a straight line. The reason for that, if you can imagine it, is you have your wheels pointing slightly towards one another at a standstill. As you go faster, there's drag forces that are trying to stop the tyre moving. They pull against the tyres and straighten them out. So it means at higher speeds your wheels are pointing straight ahead, which makes the car very stable in a straight line. The problem with that is that at those speeds, with the wheel pointing straight, it means you have a very, very low slip angle, which means low grip. That can make the car hesitant to turn in because with less slip angle, you have less grip, which means less ability to turn the car, essentially. On your rear axle, by running the toe in, particularly in larger quantities, you increase your slip angle because the wheels are pointing this way and the car wants to go straight. That can increase the grip available for acceleration. You do have a rolling resistance penalty. So like a lot of things with setup, it's about finding the compromise between grip and rolling resistance penalties, taking into account all the factors to find the optimal. Toe out does the opposite, really. As those drag forces act on the front wheels, they pull the wheels even further away from straight, which means the car can be quite unstable in a straight line, especially at higher speeds. However, because you generate quite large slip angles by having the wheels being pulled even further away from straight in a straight line, you generate a load of grip on your front tires. That can mean really aggressive turning, which is good to a point. If you put too much toe out on the front, generate too much grip, the rear end can't keep up. So the car will turn and then the rear end loses grip. And that's where oversteer comes from. For us, because we're running at really low speeds in Formula Student, running aggressive toe out on the front is a good thing, generally speaking, because we don't have the high speed stability penalty because we never reach the speeds. On the rear, your toe out does the same thing. You generate more slip, more grip, which means greater potential for acceleration, but you also induce oversteer, which for us is not necessarily a bad thing. Our course is all about agility and we don't run great distances, so we can afford to be going beyond the limits of grip in the tire. The penalty of that and the penalty of running high slip angles to create that grip is your tires wear out very quickly. But with the testing mileages and competition mileages that we do, that's something that we can probably live with. Zero toe, doesn't really have any dynamic effects. Obviously at high speeds, it will go to being slightly towed out on both wheels through the drag forces. Keeps your tires in better condition because you're not running you're not slipping them as aggressively, and you have fewer power losses, less rolling resistance through the tire. So, again, for something like drag racing where you're only in a straight line, you might want to consider running close to zero toe, but it's not really relevant for a lot of our running. So yeah, I've talked to you now about the different parameters that determine setup and kind of what they do. The next part is then implementing that setup. So we have our flat floor and our setup equipment and we can go through and do all of that. But when you're considering how a car is set up, it has to be considered when you're designing the parts that go onto it. So an important part of that is, for example, our suspension linkages. How are they supposed to be adjusted? How do you get the setup on the wheels? Historically in racing, we've been avid users of rose joints or rod ends, depending on who you ask. Now, rod ends are great because they're threaded. You put a thread in either end of your link, one left-handed, one right-handed, which means you twist the link one way, it gets longer, the other way it gets shorter. And with our setup equipment, you can then measure the effect that's having on your camber, on your toe, etc., etc. Now, they're great because they're relatively cheap. It makes the suspension really easy to adjust. It makes the car very easy to set up. But there are some negative consequences of using them. I'll throw it out to the room, see your guys' ideas on why they might not be great.
They like to get stuck.
Yes, that is part of it. Rose joints, particularly sealed rose joints that aren't serviceable. There's grease inside the bearing. The grease wears off, and then your rose joints can seize. That's a problem we faced with some of the spherical bearings in our front suspension last year. They got a bit seized up, and it made working on the car really, really difficult. Anyone else have any ideas before I? No? Oh, Aidan?
It's hard to make like a consistent change because you're just kind of rotating it by hand. It's not.
Yes, that's one of the key things. It's very difficult without expensive setup equipment that we luckily have to achieve like a meaningful setup change, because it's very difficult to do the same thing across all your links. Another disadvantage in that vein that we found last year was you have to lock off your adjustment with a jam nut, and depending on the rose joint you're using and the thread that's been made, just by tightening the jam nut you move the rose joint. So you get your setup with everything unlocked, and when you lock it the setup changes, which is not kind of what you want. It also means that it's difficult to isolate setup parameters. So when you're really trying to dial in a car, it's helpful to go, okay, we'll just change the camber now and see what that does. We'll just change the toe now and we'll see what that does. And it makes it easier to work with your driver, because even with professional drivers, they're not infallible. They get things wrong. They can have their opinions that aren't reflected in data. So in a student project where we don't have professional drivers, that can be even worse. And it means that it can be really difficult to get the car set up correctly. So for example, with our old 5-link rear suspension, it was quite good at isolating parameters, but there were certain links where if you adjusted the camber with it, it would also adjust your toe. And then if you adjust it, and if you adjust your camber a known amount, but you don't know how much you've changed your toe, you go out and drive the car, it could be a second a lap quicker, but you don't know what did it anymore. You can't say definitively it was the change in camber. Or even if you go, oh, it's a change in toe, you don't know how much the toe changed. So it's not useful information. The final thing, which is a bit of an FS UK specific problem, is design judges absolutely despise them in suspension. They have fixated on the idea that you're supposed to load them axially only. You can't put bending loads through them. So when we go to design event with rod ends, they're a bit like, why have you done that? You can't justify it. And no matter what you tell them, they won't accept it. So something to think about. So yeah, those are the kind of reasons I just went over. Another example of rod ends being a bit iffy for setup is on our front end. We can't adjust the front toe without changing the steering geometry, which is not fantastic because we want to change the toe to influence the way the car steers, but we change the geometry as well. So you then can't tell which part has caused the change. So yeah, when you're designing parts as you go through, just kind of, if it's anything to do with VD or suspension, it's just kind of stop and think about, okay, how's the part going to be adjusted, service life, lots of different factors. So yeah, that's pretty much everything I wanted to cover. That was a very introductory talk. And I'm happy to answer questions now afterwards. I would say for those of you that are interested and want to learn more, anything VD suspension, Suspension Secrets, great website, very quick, easy to digest. It's a great source of information. If any of you are really bored at night and want to know about tires and how they work, Michelin put together I wouldn't call it a textbook, it's 100 pages, but it will tell you everything you ever need to know about how a tire works and how to get performance out of your tires. So yeah, thank you everyone for listening. I'm happy to answer questions now, and thank you. Yes, Theo.
What would you use other than a rose joint to only load it actually?
So you can use encapsulated spherical bearings, which is what we have on the outside of our front wishbones currently. Judges are happier with those because you've got a big, beefy steel cage around your bearing. They don't care about the bending loads going through it because it's strong enough. The thing with encapsulated bearings is that you can't adjust them because it's a metal cage welded to the end of your wishbone. So there's a few ways around that. The way that a Formula Student judge once recommended to me, which I think is a bit absurd, is you make a set of rose joint adjustable links, go testing, work out your setup, then you create fixed encapsulated bearing copies of those links with those setup parameters that are then fixed, which from a cost perspective doesn't make sense, obviously.
You're just keeping what you've got and have already run and you know works.
Yes, exactly. So a way that we do it in Formula E and that disciplines like Le Mans prototypes and Formula One cars use is that your mounts on your upright side will be removable, and you just put metal shims that sort of match the shape of your bracket behind them. So if you have a removable lower mount and you want to put some camber on, you shim that lower mount to just put some angle on the wheel. That is great because it means you don't have the loading problems that the judges hate, and you can be much more accurate in your adjustment, because if you have a shim of a known thickness, you can work out exactly how much angle you've put on. Particularly if you're racing over a season, it's great because it means when you're telling your mechanics to set the car up, you go, put 5 shims in. They don't have to mess around achieving a certain angle with a camber gauge. They just put the shims in and it works. So that's possibly the best direction for getting certainly camber adjustment. Toe is a bit more tricky because, like with the way our steering is, you kind of just have to have adjustable length tie rods to do it. There isn't an alternative. Yes, mate?
So multi-link gives you more customizability to double wishbone, doesn't it?
Yes, it allows you to isolate the parameters that little bit better.
What other disadvantages does double wishbone have to multi-link? Or is it not
Depending on the linkage itself, it will vary from linkage to linkage. Theoretically, with 5 links, you can achieve more wheel control in terms of you can more finely tune what happens to your camber dynamically, what happens to your bump steer dynamically. That's not to say like you can make a double wishbone setup that has better wheel control than a 5-link. It's just theoretically with enough time and like enough R&D, you can make a 5-link that little bit more refined. But really, like our old 5-link setup, which was 5 distinct links, is like crazy overkill and way too complex. Because if we never understood it, which meant we couldn't take advantage of it. And if you look at a Formula One car or our Formula E car, we have multi-link, but it's just double wishbone with an extra link that isolates your toe, so you can adjust toe completely independently, which is, yeah, I don't want to make too broad conclusions, but if Formula One has settled on that as the solution, I think it's a pretty good solution.
If you're in a situation where you have like fairly limited testing time for a competition, what do you say like the first like crucial like dynamic setup parameters to visit?
Well, I would say before you start looking at setup, the most important thing is data. Get your data acquisition working, get some good data logging software. I would recommend, I know we've been using Race Studio, which is a bit shit, excuse the term. The 2 main telemetry softwares that are used in industry are WinTax and Atlas. WinTax has a student version, so I'd get on that if I was you. You don't need tons and tons of sensors. Stuff like the damper travels, I would say, is like the most important thing you get working on the car. With the damper travels and enough sort of maths with the suspension, you can work out exactly what the car's doing dynamically. With like the roll couple distribution I was talking about, and you can see how the wheel travels are influenced by various factors. If you get your damper travel and some models working, and your TPMS reading pressures and carcass temperatures, and your IMU reading your lateral and longitudinal G, that's all the information you then need to go and look at setup. I would say, I know from my discussions this year that the goal of the suspension system is that when the links go on the car with no adjustment, everything's at 0, which is great. That's perfect, because it gives you a completely blank slate to go from. I would say before the car goes out, you'd statically set it up with a little bit of negative camber. A little bit of probably toe out on both axles. Depends on what you're aiming for. Start with a very conservative baseline setup, and as conservative as you possibly can. Put like a degree or less of each of the parameters on. You go out, see what the maximum grip level you're getting through your GG diagram is. See if your tyres are getting into the window, which you can work out beforehand. Don't want to give you too much work, Eric, but From there, you then go one at a time. Camber's normally a good one to start with, because it's generally quite predictable when you're adding negative camber what's going to happen. The car will get grippier and grippier and grippier up to a point where you go too far and you lose the grip again. So by scanning with your like GG data and your roll couple, because you can see if the car's under or oversteering, you can then go, okay, we're getting more and more and more grip. Then it falls away, and then you know that like somewhere between those 2 points, that's where your optimum is. Toe, because it's linked with steering geometry, will then be a little bit more ad hoc in terms of still look and see like, okay, if we do this to the toe out, it makes the car turn really quickly, which brings like your roll center distribution backwards, makes the car oversteery, which is probably what we'd be aiming for. So you get your toe set up so that you get the car behaving in the right sort of balance between over and understeer. Make sure you can get around your hairpins and that kind of stuff. This year with our new motor, we should be able to induce some oversteer with a bit of right foot, which makes life easier. Caster is a little bit kind of, you set it up, and with double wishbones, it's always going to be linked to your camber changes. You'd have a ballpark figure, probably around 5 degrees, something like that you'd want to be at. And then as long as you're not making huge changes with the rest of your setup, that should be optimal. But yeah, the main thing is when I look at like a test I would go on with Formula E is you're always really conservative. Start small, make little changes to find your sweet spot. Yeah, when it comes to setup changes at an in-person test, it's a little bit difficult for you guys because you don't have a garage to work in. So geometry changes are pretty much impossible without a flat floor. So the solution to that is you can buy flat patches, which you can set up with lasers and stuff, so you always have a flat floor. But that's a bit of a James problem, I would think. Yes, Will.
Are you enjoying yourself at the track?
Yes, mate. I'm absolutely loving it. Yeah, I don't want to talk about my placement the whole time when we're doing Q&A. If people want to talk to me afterwards, that's completely fine. But yeah, does anyone have any questions to do with what I've just talked about? Yes, Theo.
Would it be worth having a competition, just 2 setups, one for the acceleration and maybe braking, and you switch to the one for skid pad?
Yeah, exactly. With the way the event is structured, you have enough time after acceleration to change your setup. So yeah, it's definitely worth that testing, doing an isolated block of setup work to work out your optimal acceleration setup, which would mainly be focused on camber and toe and tire pressures. Once you've got that zeroed in, make sure it gets noted down properly somewhere with all the parameters. Then you do your next block of testing, and the similarities between autocross, sprint, and endurance means you have another setup that would work really well for that. Okay. I think that's everyone's questions answered.
Thank you very much, that was wonderful.
Oh, yes, thank you everyone for coming. It's great to see some new faces involved in the project. And yeah, I'll be here if people want to talk to me individually for any reason. And yeah, thank you everyone for taking the time.